The universe is vast beyond human comprehension, filled with objects ranging from the infinitesimally small to the incomprehensibly large. To understand what could possibly be considered the largest thing in existence, scientists first need a way to measure size. Unlike everyday objects, where we can use rulers, tape measures, or scales, the largest things in the universe cannot be grasped or weighed directly. Instead, astronomers, physicists, and cosmologists rely on observational data, sophisticated instruments, and fundamental principles of physics to determine the dimensions, mass, and reach of cosmic objects. Defining largest is surprisingly complex, because size can be measured in multiple ways, by volume, mass, diameter, gravitational influence, energy content, or even the spatial area an object occupies. Each measure provides a different perspective on what it means to be large. On Earth, measurement is straightforward. Mountains, oceans, and cities can be measured in meters or kilometers. Mount Everest, the tallest peak on Earth above sea level, rises 8,848 meters. Mauna Kea in Hawaii, when measured from its base on the seafloor, reaches 10,210 meters, making it the tallest mountain from base to peak. The Mariana Trench, the deepest part of the ocean, plunges to 10,924 meters below sea level. These examples provide measurable extremes of size on Earth. As we look beyond Earth, scales increase. The largest planet in our solar system, Jupiter, has a diameter of 139,820 kilometers, roughly 11 times that of Earth. Jupiter's mass, 1.9 times 10, 27 kilograms, is more than twice the mass of all other planets combined. Its gravitational influence extends far beyond its atmosphere, shaping the asteroid belt and affecting other planets' orbits. Saturn, the second largest planet, is slightly smaller in mass and has rings that span up to 282,000 kilometers. Even a planet with a smaller diameter can dominate a region of space due to gravity. When scientists measure stars, complexity increases. The Sun, a medium-sized yellow dwarf, has a diameter of approximately 1.39 million kilometers and a mass of 1.989 times 1030 kilograms. The Sun contains 99.86% of the mass of the solar system. Its gravitational influence extends beyond the planets, affecting the Oort cloud, a shell of icy bodies that may reach 100,000 astronomical units from the Sunday. Cometary fragments at the edge of the solar system are under the Sun's gravitational control. Volume and mass alone are insufficient to describe its full influence. The tools for measuring large cosmic objects have evolved. Telescopes, from Galileo's refracting instrument to the Hubble Space Telescope, allow determination of size by observing light. Apparent brightness, distance, and movement provide data to calculate dimensions. Radio telescopes like the Very Large Array detect gas clouds and galactic structures invisible to optical light. Infrared and X-ray telescopes, such as Spitzer and Chandra, reveal star-forming regions and hot plasma in galaxy clusters. Surveys like the Sloan Digital Sky Survey have mapped millions of galaxies, providing a view of large-scale cosmic structures. By combining multiple wavelengths, scientists can measure visible and invisible mass shaping the universe. Distance adds complexity. The further we look, the longer light takes to reach us. Observing galaxies billions of light years away shows them as they existed billions of years ago. The observable universe, the region from which light has reached Earth since the Big Bang about 13.8 billion years ago, has a radius of approximately 46.5 billion light-years. It contains an estimated 2 trillion galaxies, each with hundreds of billions of stars. Measuring size at this scale involves spatial dimensions and light travel time. Size is contextual. Sagittarius A star, the supermassive black hole at the Milky Way's center, contains roughly 4.3 million solar masses within a radius of 0.08 light-years. Its mass is large, yet its volume is small compared to a star cluster or galaxy. The largest stars, such as UY Scuti and VY Canis Majoris, can exceed 2 billion kilometers in diameter, larger than Jupiter's orbit, but have masses only tens of times that of the Sunday. Measuring size by volume or mass alone can be misleading. Gravitational reach and energy output are also relevant. Size can also be defined by grouping objects. Stars form clusters, galaxies, and larger structures, such as galaxy clusters and superclusters. The Milky Way spans about 100,000 light-years in diameter, containing over 100 billion stars and a halo of dark matter extending several 100,000 light-years. Our galaxy is part of the Local Group, a collection of over 50 galaxies, which is part of the Laniakea supercluster, spanning roughly 520 million light-years. These groupings show size in terms of collective structures and spatial extent. Energy output can define size. A supernova, the explosive death of a massive star, can release more energy in a few days than the Sun will emit in its 10 billion year lifetime. Gamma-ray bursts, lasting milliseconds to minutes, emit more energy than hundreds of supernovae combined. These phenomena affect regions of space many light-years away. Ultimately, measuring the largest objects requires attention to scale, technique, and perspective. Instruments on Earth and in space provide data, and interpretation relies on gravitational physics, nuclear processes, and cosmology. Observations must be corrected for distance, light travel time, redshift, and intervening matter. Databases like NASA's Extragalactic Database, ESA catalogs, and the Simbad Astronomical Database allow researchers to compile measurements of stars, galaxies, and large-scale structures for comparison. Objects from particles to planets, stars to galaxies, are measured using different criteria. Volume, mass, energy output, gravitational reach, and spatial extent provide quantitative ways to compare size. The Sun contains most of the solar system's mass, the Milky Way contains over 100 billion stars, and the Laniakea supercluster spans roughly 520 million light-years, the smallest giant's minimum physical scales. Before the vast expanse of galaxies and superclusters, before even the planets or stars, there is the universe on the tiniest measurable scale. To understand the largest things, scientists first need to understand the foundation from which size emerges. This is the world of fundamental particles, quantum fluctuations, and the building blocks of matter. Here, scale is measured in billionths of a meter or smaller, where distances are so minuscule that intuition becomes almost useless. Yet these small scales are critical, because every massive structure in the universe, from planets to clusters of galaxies, originates from these tiny entities. At the very beginning are quarks, which combine to form protons and neutrons. Quarks are estimated to have sizes less than 10⁻19 meters, essentially point-like for practical measurement purposes. There are 6 types, known as flavors: the up, down, charm, strange, top, and bottom. Each contributes differently to the properties of matter, such as mass, charge, and interaction via fundamental forces. Protons and neutrons, composed of 3 quarks each, are slightly larger, roughly 0.84 to 0.87 femtometers in radius. These particles contain almost all the mass of ordinary matter. Electrons, another key particle, are far lighter and smaller than protons. They are generally treated as point particles in the standard model of particle physics, with no measurable radius so far. Their mass is approximately 9.11 times 10⁻31 kilograms compared to 1.6 7 times 10 negative 27 kilograms for a proton. Electrons determine chemistry, electricity, and the formation of molecules, which are essential components of stars, planets, and matter. Moving up in scale, atoms form when electrons orbit nuclei, which are clusters of Qa protons and neutrons. A hydrogen atom, the simplest and most abundant, has a radius of roughly 53 picometers. More complex atoms, like uranium, have radii several times larger, but still under 1 nanometer. Atomic arrangements dictate the properties of solids, liquids, and gases, and atomic bonding determines chemical and structural diversity. Molecules represent the next tier. Water has a molecular size of about 0.275 nanometers. Complex biological molecules, such as proteins, DNA, and RNA, can reach hundreds of nanometers in length and span thousands of atoms. A strand of human DNA is approximately 2 nanometers in diameter, but can stretch over 2 meters if fully unraveled. These structures are invisible without electron microscopes, and molecules form larger objects such as rocks, oceans, and biological tissues. Even smaller than atoms and molecules is the domain of subatomic forces. Gluons, photons, and W and Z bosons carry the interactions that bind matter and govern energy transfer. Gluons, responsible for holding quarks together in protons and neutrons, act over distances less than 10 negative 15 meters. Photons mediate electromagnetic force, have no rest mass, and travel at light speed, interacting with matter over large distances. Neutrinos, nearly massless particles produced in stars and supernovae, can pass through entire planets without interacting. In 1 second, trillions of neutrinos from the Sun pass through the human body. Size at the quantum level is influenced by principles that differ from everyday scales. The Heisenberg uncertainty principle dictates that position and momentum cannot both be precisely known. At scales smaller than atoms, size is probabilistic, a range of potential locations rather than a defined boundary. Quantum fluctuations in the vacuum create transient particles that appear and disappear quickly. These fluctuations occur on scales as small as 10 negative 35 meters. Cosmic rays, high-energy particles originating from outside the solar system, provide a view into small-scale physics. Composed primarily of protons and atomic nuclei, they travel at nearly the speed of light. Some, such as the Oh My God particle observed in 1991, carried energy equivalent to a baseball, traveling at 90 kilometers per hour, but concentrated in a single proton. Density is an important factor at small scales. Neutron stars, although macroscopic, are collections of neutrons packed so tightly that a sugar cube-sized portion would weigh about 1 billion tons on Earth. Even a microscopic neutron, when multiplied and compressed, contributes to objects that are small in diameter but have high mass and gravitational strength. The formation of matter in the early universe occurred at small scales. Within the first few minutes after the Big Bang, protons and neutrons combined in nucleosynthesis, forming hydrogen, helium, and trace amounts of lithium. These nuclei then combined with electrons to form the first neutral atoms about 380,000 years later, during recombination. This process allowed light to travel freely, creating the cosmic microwave background radiation observed today. Advances in technology have allowed scientists to measure these tiny scales more precisely. Particle accelerators, like the Large Hadron Collider in Switzerland, collide protons at energies exceeding 13 tera-electronvolts, revealing subatomic behavior and confirming the existence of particles such as the Higgs boson. Detectors such as ATLAS and CMS track billions of collisions, providing data on particle lifetimes, mass, and interaction probabilities. Even at small scales, there are extremes. Muons, heavier cousins of electrons, exist briefly before decaying into lighter particles. Pions and kaons, types of mesons, mediate strong interactions influencing nuclear forces. Strange quarks appear inside exotic particles called hyperons. Some theorized particles, like axions or dark matter candidates, remain undetected but may contribute significantly to the mass of the universe. The world of particles, atoms, and molecules forms the basis of larger structures, from planets to stars, galaxies, and clusters. The properties and interactions of these small components contribute to the formation of stars, galaxies, and large-scale cosmic structures. Variations in mass, energy, or particle interactions at small scales influence the development of larger structures, while differences in proton mass or early density fluctuations affected the formation and distribution of galaxies and stars, atoms, molecules, and the scale of matter. From the realm of subatomic particles, the next leap in size is the world of atoms. While quarks, electrons, and protons define the foundation of matter, atoms represent the first truly independent units that can exist in isolation, combine, and build structures visible to the human eye or detectable with laboratory equipment. These tiny entities mark the transition from the abstract microscopic world of forces and probabilities to a tangible scale where matter takes recognizable forms. Understanding atoms is essential because they are the building blocks of everything we see, from the iron in Earth's core to the hydrogen in distant nebulae. Hydrogen, the simplest and most abundant element in the universe, consists of one proton and one electron. Its atomic radius is roughly 53 picometers. Helium contains 2 protons, 2 neutrons, and 2 electrons, giving it an atomic radius of about 31 picometers for the nucleus and 31 picometers for the electron cloud. Helium's chemical inertness allows it to accumulate in stars, providing fuel for nuclear fusion. Heavier elements such as oxygen, carbon, nitrogen, and iron participate in chemical reactions and form molecules, solids, and planetary materials. Atomic nuclei are incredibly dense, packing nearly all of an atom's mass into a space smaller than a femtometer. Surrounding electrons occupy a much larger cloud, making the atom mostly empty space. This structure allows atoms to form bonds without their nuclei colliding, enabling molecules. Water molecules consist of 2 hydrogen atoms bonded to an oxygen atom with a bond length of about 95.7 picometers. In a single drop of water, there are approximately 1.67 times 10^21 molecules, each occupying only a few cubic angstroms. Molecules vary in complexity. Simple diatomic molecules like oxygen or nitrogen have lengths of about 120 picometers and masses of approximately 32 and 28 atomic mass units, respectively. More complex molecules, such as glucose or C6H12O6, contain dozens of atoms and measure about 1 nanometer across. Larger molecules, like hemoglobin, a protein responsible for oxygen transport, can span up to 6 nanometers and consist of over 9,000 atoms. The arrangement of molecules leads to the formation of crystals and solids. Diamonds, composed entirely of carbon atoms, can have lattices extending thousands of atoms in 3 dimensions, with a density of about 3.5 grams per cubic centimeter. Salt crystals, composed of sodium and chloride ions, form repeating cubic structures with individual ions separated by about 282 picometers. Billions of these atoms can fit into a single grain of sand. Liquids demonstrate specific properties based on atomic and molecular arrangement. Water, with a density of roughly 1 gram per cubic centimeter, exhibits strong hydrogen bonding that affects its boiling point, surface tension, and solvent properties. Mercury, a liquid metal at room temperature, has a density of 13.53 grams per cubic centimeter due to tightly packed atoms, while liquid helium remains a superfluid at temperatures below 2.17 Kelvin. Atomic and molecular size affects the behavior of light and electromagnetic radiation. The spacing of atoms in crystals can produce diffraction patterns, which scientists use to determine molecular structures with X-ray crystallography. The wavelengths of visible light, ranging from 400 to 700 nanometers, are thousands of times larger than individual atoms, making them invisible to the naked eye. Electron microscopes, capable of resolving objects as small as 50 picometers, reveal molecular structures such as the double helix of DNA and the folded shapes of proteins. The abundance of elements across the universe shows how atoms combine to form macroscopic matter. Hydrogen and helium together make up more than 98% of the baryonic matter. Carbon, oxygen, and nitrogen, though less abundant, participate in chemical reactions and form planetary materials. Iron, nickel, and silicon, formed in the cores of massive stars and dispersed through supernovae, constitute the bulk of terrestrial planets. A single iron atom weighs approximately 9.27 times 10, -26 kilograms, and Earth's core contains roughly 1.9 times 10^51 iron atoms. Molecules and atoms dictate thermal and chemical dynamics. In the Sun, hydrogen atoms fuse into helium at millions of degrees Kelvin, releasing energy and producing elements up to iron through nuclear fusion. In the cold interstellar medium, molecules such as carbon monoxide, ammonia, and formaldehyde form in icy dust clouds, which can span dozens to hundreds of light years and serve as star-forming regions. Atomic and molecular organization underlies biological complexity. The human body, with roughly 7 times 10^27 atoms, assembles into macromolecules, organelles, cells, tissues, and organs. Proteins, lipids, nucleic acids, and carbohydrates interact across nanometer to micrometer scales to sustain life processes. The brain contains over 86 billion neurons, each with thousands of synapses, forming a network of molecular and cellular structures. Atoms and molecules combine into larger objects with properties that emerge from atomic arrangements and interactions. Strength, elasticity, magnetism, and conductivity arise from these structures. Materials like steel, silicon, and ice exhibit properties relevant for technology, construction, and geological processes. Geological structures, such as mountains and tectonic plates, derive characteristics from their constituent atoms and molecules. Atomic spacing determines material density, molecular geometry governs chemical reactivity, and bonding types influence mechanical strength. Through spectroscopy, scientists detect wavelengths absorbed or emitted by atoms and molecules, allowing identification of elements in stars, nebulae, and exoplanets. Instruments such as the Atacama Large Millimeter or Submillimeter Array observe molecular clouds and chemistry in star-forming regions thousands of light-years away. Atoms and molecules form the first level of tangible structure in the universe. Through combination and organization, they produce matter observable with instruments. These structures contribute to larger formations, such as planets, stars, and galaxies, mountains, oceans, and the largest structures on Earth. After exploring the microscopic foundation of the universe in atoms and molecules, we now turn our attention to the largest tangible structures found on our own planet. Earth, while minuscule compared to stars and galaxies, presents a range of enormous formations that are measurable, observable, and surprisingly diverse. Mountains, oceans, rivers, and continents offer a striking contrast to the subatomic and atomic scales previously discussed. Studying these structures allows us to appreciate the principles of size and scale in a context that is accessible and immediate, yet still awe-inspiring when measured quantitatively. Mountains represent some of the largest terrestrial structures. Mount Everest, in the Himalayas, reaches 8,848 meters above sea level. Mauna Kea in Hawaii measures 10,210 meters from its base on the seafloor. Mountains such as K2, Kangchenjunga, and Lhotse, all above 8,500 meters, are part of the Himalayan chain, which extends over 2,400 kilometers across Asia. Mountains are not only tall, but also massive. The mass of Mount Everest is estimated at around 161 trillion kilograms. They are composed of layers of rock compressed over hundreds of millions of years through tectonic activity. The Himalayas formed as the Indian plate collided with the Eurasian plate about 50 million years ago, a process that continues today, causing uplift and seismic activity. The Andes stretch 7,000 kilometers along South America's western edge. Oceans represent vast volumes of liquid. The Pacific Ocean covers 168.7 million square kilometers and reaches 10,924 meters at the Mariana Trench. Its estimated volume of 710 million cubic kilometers contains about 1.335 times 1018 metric tons of water. The Atlantic Ocean, covering 85.1 million square kilometers, has depths exceeding 8,000 meters in areas such as the Puerto Rico Trench. Ocean currents, including the Gulf Stream and Antarctic Circumpolar Current, circulate water and distribute heat and nutrients. Continents provide large-scale landforms. Africa covers about 30.37 million square kilometers and contains the Sahara Desert, which spans 9.2 million square kilometers. Asia, at 44.58 million square kilometers, contains Mount Everest, the Gobi Desert, and the Yangtze River, 6,300 kilometers long. Antarctica spans 14 million square kilometers and contains 26.5 million cubic kilometers of ice, holding roughly 60% of global freshwater. Plate tectonics underlies many large-scale features. Earth's lithosphere has roughly 15 major tectonic plates, including the Pacific, North American, Eurasian, African, and Antarctic plates. These plates move at rates of 2 to 15 centimeters per year, colliding, sliding, and separating to form mountains, ocean basins, and trenches. The Pacific Plate covers about 103 million square kilometers, approximately a quarter of Earth's surface. Plate movements generate earthquakes, volcanic eruptions, and tsunamis. Volcanoes, as concentrated features, also exemplify large structures. Mauna Loa, located on Hawaii's Big Island, covers an area of about 5,271 square kilometers and rises 9,144 meters from its base, making it the most massive single volcano on Earth. Its eruptions have been recorded for centuries, with lava flows reshaping the surrounding landscape. Similarly, Mount Fuji in Japan rises 3,776 meters and serves as a landmark of both geological and cultural significance. The formation and growth of volcanoes are controlled by magma chamber dynamics, pressure buildup, and plate movements, linking small-scale subterranean processes to enormous visible structures. Rivers and deltas, though elongated rather than vertical, also rank among the largest terrestrial formations. The Nile River, at approximately 6,650 kilometers, is the longest river on Earth, while the Amazon River carries the largest volume of water, averaging about 209,000 cubic meters per second. The Amazon basin spans roughly 7 million square kilometers and contains hundreds of tributaries. River deltas, such as the Ganges-Brahmaputra-Meghna Delta, can cover tens of thousands of square kilometers through sediment deposition from multiple river systems. Deserts provide another scale of size, defined by spatial extent rather than volume. The Antarctic desert, classified as a polar desert, covers approximately 14 million square kilometers, while the Sahara Desert, the largest hot desert, spans about 9.2 million square kilometers. Sand dunes within deserts can exceed 180 meters in height, formed by wind-driven accumulation of sand over long periods. Desert regions are shaped by atmospheric circulation, aridity, and sediment transport processes. Glaciers are among the most massive structures on Earth. The Lambert Glacier in Antarctica stretches approximately 400 kilometers in length and 100 kilometers in width, making it the largest glacier by area. Glaciers flow under gravity, eroding bedrock and transporting sediment. Greenland's ice sheet covers about 1.71 million square kilometers and contains an estimated 2.85 million cubic kilometers of ice, sufficient to raise global sea levels by more than 7 meters if fully melted. Individual rock formations and canyons can reach substantial dimensions. The Grand Canyon in Arizona extends 446 kilometers in length and reaches depths exceeding 1,800 meters, exposing nearly 2 billion years of geological strata. Uluru in Australia rises 348 meters above the surrounding desert and extends approximately 9.4 kilometers in circumference. The mass of Uluru is estimated at around 6 million tons, resulting from long-term geological processes, including erosion and uplift. Mountain ranges influence river drainage patterns, while rivers transport sediment to oceans. Ice sheets store fresh water that contributes to sea level variation through melting and accumulation cycles. Volcanic activity modifies regional topography, and tectonic plate motion reshapes continents and ocean basins over geological time. These processes operate through measurable variables such as elevation, surface area, volume, and mass. Humans have constructed large-scale features relative to local environments. The Great Wall of China extends approximately 21,196 kilometers in length. Engineering projects such as cities, dams, and reservoirs, including the Three Gorges Dam, which holds about 39.3 billion cubic meters of water, alter landscapes at regional scales. These structures are limited in spatial extent and volume when compared with major natural geological formations. Scientists measure Earth's large-scale structures using parameters such as height, volume, area, and mass. Instruments including satellites, sonar mapping systems, LiDAR, and GPS provide precise spatial data. Remote sensing techniques identify underwater mountain ranges, ocean trenches, and ice formations. Geological records and tectonic data are used to document the distribution and dimensions of major terrestrial features. Mountains, oceans, and glaciers represent Earth's largest macroscopic surface features. Their formation is governed by measurable physical processes, including gravity, plate tectonics, erosion, and hydrological circulation. These processes operate through quantifiable properties such as rock density, crustal thickness, water volume, and elevation change over geological timescales. The dimensions of these terrestrial features provide reference points for comparing Earth's surface structures with larger bodies within the solar system, gas giants, and planetary titans. Having explored the largest structures that exist on Earth, the next step in scale takes us beyond the limits of a single planet's surface and into the realm of planets themselves. While Earth's mountains, oceans, and tectonic plates represent the maximum scale achievable on a rocky world, they are modest when compared to the largest planets in the solar system. Gas giants and ice giants dominate planetary size, mass, and volume, revealing how dramatically scale increases once gravity gathers vast amounts of material during planetary formation. The largest planet in the solar system is Jupiter, a gas giant with a diameter of approximately 139,820 kilometers at its equator. This is more than 11 times Earth's diameter and gives Jupiter a volume large enough to contain over 1,300 Earth-sized planets. Its mass, about 1.9 times 1027 kilograms, exceeds the combined mass of all other planets in the solar system by more than a factor of 2. Despite this enormous mass, Jupiter's density is only about 1.33 grams per cubic centimeter, much lower than Earth's, reflecting its composition of hydrogen and helium rather than rock and metal. Jupiter's immense size is not limited to its visible atmosphere. Its gravitational influence extends far beyond the planet itself, shaping the orbits of nearby asteroids and stabilizing regions of the solar system. Jupiter's Hill sphere, the region where its gravity dominates over the Sun's influence for orbiting objects, extends roughly 53 million kilometers in radius. This allows Jupiter to host at least 95 known moons, including Ganymede, the largest moon in the solar system, which itself has a diameter of 5,268 kilometers and is larger than the planet Mercury. Saturn, the second largest planet, has a diameter of about 116,460 kilometers and a mass of 568 times 1026 kilograms. While significantly less massive than Jupiter, Saturn is remarkable for its extremely low density, approximately 0.69 grams per cubic centimeter, meaning it would theoretically float in water if a body of water large enough existed. Saturn's volume is sufficient to contain over 760 Earths. Its vast system of rings extends up to 282,000 kilometers from the planet's center, forming a structure larger than Earth itself. These rings, composed of ice and rock fragments ranging from micrometers to tens of meters in size, collectively contain a mass comparable to a medium-sized moon. Beyond the gas giants lie the ice giants, Uranus and Neptune, which, while smaller, still dwarf terrestrial planets. Uranus has a diameter of approximately 50,724 kilometers and a mass of 8.68 times 1025 kilograms. Neptune is slightly smaller in diameter at 49,244 kilometers, but more massive, with a mass of 1.02 times 1026 kilograms. Both planets are composed largely of water, ammonia, and methane ices mixed with hydrogen and helium, giving them higher densities than Jupiter and Saturn. Neptune's density is about 1.64 grams per cubic centimeter, reflecting this heavier composition. Neptune holds the record for the strongest winds observed in the solar system, reaching speeds of over 2,100 kilometers per hour. These winds occur within an atmosphere that extends thousands of kilometers above the planet's interior. Uranus, with an axial tilt of approximately 98 degrees, rotates with its rotational axis nearly parallel to its orbital plane while maintaining an extensive atmosphere. The atmospheres of gas and ice giants extend tens of thousands of kilometers beyond their deeper layers. One of the most striking differences between gas giants and rocky planets lies in internal structure. Unlike Earth, which has a solid surface, gas giants transition gradually from atmosphere to dense fluid and eventually to a compact core. Jupiter's core is estimated to contain between 10 and 15 times Earth's mass, surrounded by layers of metallic hydrogen under pressures millions of times greater than Earth's atmospheric pressure. These internal layers contribute significantly to the planet's overall radius and mass distribution. The lack of a solid surface makes defining the edge of a gas giant complex, as atmospheric density decreases gradually rather than abruptly. Magnetic fields provide another measurable aspect of planetary extent. Jupiter possesses the strongest planetary magnetic field in the solar system, extending up to 7 million kilometers toward the Sun and nearly reaching Saturn's orbit on the opposite side. This magnetosphere is the largest continuous structure in the solar system aside from the heliosphere. Saturn, Uranus, and Neptune also possess magnetospheres with varying sizes and geometries, determined by internal dynamics and solar wind interaction. The formation of gas giants explains why they dominate planetary scale. During the early stages of the solar system, regions beyond the frost line allowed volatile compounds to condense, enabling planetary cores to grow rapidly. Once these cores reached a critical mass, they began accreting hydrogen and helium from the surrounding protoplanetary disk. Jupiter likely formed within the first few million years of the solar system's existence, growing quickly enough to capture enormous amounts of gas before the disk dissipated. This rapid growth explains why gas giants are so much larger than terrestrial planets, whose formation was limited by the availability of heavier elements. Earth's diameter of 12,742 kilometers is much smaller than Uranus, which is approximately 4 times larger. Earth's mass, 5.97 times 10^24 kilograms, is less than 1/300th of Jupiter's mass. Terrestrial features such as mountain ranges and ocean basins occupy relatively small fractions of planetary radii, measured in tens of thousands of kilometers. Gas giants also play a crucial role in shaping entire planetary systems. Jupiter's gravity likely influenced the distribution of material during planet formation, preventing a planet from forming in the asteroid belt and affecting the orbits of Mars and Earth. Saturn's moons, including Titan, which has a dense atmosphere thicker than Earth's, demonstrate how planetary mass enables the formation of complex satellite systems. Uranus and Neptune, though smaller, still host moons with diameters exceeding 1,500 kilometers, each representing planetary-scale objects in their own right. Observations of exoplanets show that planets larger than Jupiter exist in other star systems. Astronomers have identified hot Jupiters with radii up to 1.7 times that of Jupiter, orbiting close to their host stars. Some of these planets have masses several times greater than Jupiter's, while others exhibit expanded atmospheres due to intense stellar heating. Gas giants are limited in mass by planetary formation processes and gravitational equilibrium. Jupiter does not contain sufficient mass to initiate sustained nuclear fusion. Objects exceeding this mass threshold enter the category of brown dwarfs or stars, defined by their ability to generate energy through fusion reactions. Gas giants possess large diameters, masses, atmospheres, magnetic fields, and gravitational domains relative to terrestrial planets. Their physical limits are defined by planetary formation mechanisms and the inability to sustain nuclear fusion. Objects exceeding planetary mass thresholds transition into brown dwarfs or stars, distinguished by fusion-driven energy production. The Sun and the dominance of stars. After examining the largest planets and the limits of planetary growth, the next step in scale moves into a category where size, mass, and energy output increase dramatically. Stars represent a fundamental shift in the hierarchy of existence. Unlike planets, stars generate their own energy, sustain internal nuclear reactions, and influence space far beyond their visible boundaries. To understand stellar dominance, the most logical reference point is the Sun, the star that defines the scale of our solar system and provides a measurable bridge between planets and far larger stellar objects. The Sun is classified as a G-type main sequence star and contains approximately 99.86% of the total mass of the solar system. With a diameter of about 1.39 million kilometers, it is roughly 109 times wider than Earth and 10 times wider than Jupiter. Its volume is large enough to contain over 1 million Earth-sized planets. This immense size is matched by its mass, which reaches nearly 2 × 10^30 kilograms, placing it far beyond anything that planets can achieve through gravitational accumulation alone. Even the largest gas giants fall short of the threshold needed to initiate sustained nuclear fusion, a defining property of stars. The Sun's interior structure enables energy generation. At its core, temperatures exceed 15 million degrees Celsius, and pressures allow hydrogen nuclei to fuse into helium. This fusion process releases energy that travels outward through radiative and convective layers before emerging as sunlight. Each second, the Sun converts approximately 4 million tons of mass into energy, a quantity negligible relative to its total mass. Based on its current fusion rate, the Sun is expected to remain on the main sequence for approximately 10 billion years. Beyond its physical size, the Sun's influence extends across an enormous region of space. The solar gravitational field governs the orbits of planets, dwarf planets, asteroids, and distant icy bodies. Its radiation pressure and solar wind shape the heliosphere, a vast bubble of charged particles extending more than 120 astronomical units in all directions. This region forms a protective boundary that shields the solar system from a significant portion of interstellar radiation. The heliosphere's diameter exceeds 18 billion kilometers, making the Sun's effective domain vastly larger than its visible surface. The Sun's magnetic field is generated by plasma motion within its interior and drives solar activity such as sunspots, flares, and coronal mass ejections. Sunspots can reach tens of thousands of kilometers in diameter, while solar flares release large quantities of energy over short timescales. Coronal mass ejections expel billions of tons of plasma into space, interacting with planetary magnetospheres and upper atmospheres. These magnetic phenomena extend well beyond the Sun's visible surface. The Sun emits approximately 3.8 × 10^26 watts of power. A fraction of this energy reaches Earth, driving atmospheric circulation and ocean currents. Planets do not generate comparable energy internally and primarily reflect or redistribute incident radiation. Sustained nuclear fusion distinguishes stars from planetary bodies in terms of energy output. The Sun also serves as a benchmark for comparing other stars. Astronomers use solar mass, solar radius, and solar luminosity as standard units to describe stellar properties across the galaxy. Even stars considered small are often comparable to or larger than the Sun, while massive stars can exceed it by orders of magnitude. By understanding the Sun's size and behavior, scientists establish a reference framework that allows meaningful comparison between stars of vastly different scales. Stellar size affects fuel consumption rates and lifespan. Smaller stars, such as red dwarfs, consume hydrogen slowly and can persist for trillions of years, while larger stars exhaust fuel rapidly and may end as supernovae within millions of years. The Sun falls between these extremes in mass and lifespan. Stellar evolution models relate mass to fusion rate, luminosity, and lifespan. The Sun's mass also warps space-time in a measurable way. Its gravitational field bends light from distant stars, an effect first confirmed during the solar eclipse of 1919, providing early experimental support for general relativity. This bending is subtle compared to that produced by more massive stars or black holes, but it underscores how stellar mass influences the geometry of space itself. Planets, even the largest ones, do not produce measurable gravitational lensing effects under normal conditions. Observational techniques reveal the true scale of the Sun with remarkable precision. Helioseismology measures oscillations on the Sun's surface to probe its internal structure, mapping temperature, density, and rotation deep within its interior. Space-based observatories, such as SOHO and the Solar Dynamics Observatory, continuously monitor solar activity, capturing detailed images of surface features and magnetic loops that dwarf Earth in size. These observations show that even the Sun's smallest visible features often exceed planetary dimensions. The Sun's diameter exceeds the orbital spacing of some compact exoplanetary systems. In several observed systems, planets orbit closer to their host stars than Mercury orbits the Sun, completing orbits in a few days. Stellar gravity governs orbital spacing and system architecture in these cases. The Sun is not isolated, but part of a larger stellar population within the Milky Way. It orbits the galactic center at a distance of about 26,000 light-years, completing one full orbit every 230 million years. Even within this context, the Sun remains a significant mass concentration, interacting gravitationally with nearby stars and interstellar material. Its motion through the galaxy carries the heliosphere through varying environments, influencing the influx of cosmic rays and interstellar particles into the solar system. The Sun is composed primarily of hydrogen and helium, with heavier elements accounting for approximately 2% of its mass. These heavier elements originated in earlier generations of stars and were incorporated into the solar nebula prior to the Sun's formation. Stellar composition measurements are used to trace nucleosynthesis and chemical enrichment processes. Some stars have masses several times greater than the Sun and radii tens or hundreds of times larger. The Sun is the most extensively studied star, providing well-defined values for mass, radius, luminosity, and composition. These parameters are used to distinguish stars from planets based on fusion capability. Stars generate energy through sustained nuclear fusion and exert gravitational influence over extensive regions of space. While the Sun contains the majority of the solar system's mass and energy output, stellar mass and fusion processes, on the other hand, distinguish stars from planetary bodies. The Sun serves as a reference for stellar mass, radius, luminosity, and internal structure. Measurements of larger stars are compared against solar values to quantify differences in scale. Some stars possess radii large enough to encompass the orbital distances of inner planets in compact planetary systems, red giants, supergiants, and hypergiants. With the Sun established as the baseline for stellar size and dominance, the next escalation in scale comes from stars that grow far beyond their initial dimensions. While the Sun will remain relatively stable for billions of years, many stars undergo dramatic expansion during their lifetimes, transforming into red giants, supergiants, and in the most extreme cases, hypergiants. These stars redefine size in ways that surpass planetary systems, stretching the limits of how large a single star can become before gravity and instability bring its evolution to an end. Red giants represent the first major expansion phase in stellar evolution. When a star exhausts the hydrogen fuel in its core, nuclear reactions shift outward, causing the outer layers to expand. A star with a mass similar to the Sun can increase its radius by more than 100 times during this phase. When the Sun becomes a red giant in roughly 5 billion years, its outer atmosphere is expected to expand beyond the orbit of Mercury and possibly engulf Venus. The star's mass remains largely unchanged, while its volume increases substantially. More massive stars undergo even more extreme transformations. Supergiants form from stars with initial masses at least 8 times that of the Sunday. These stars expand to sizes that dwarf the orbits of inner planets. Betelgeuse, a red supergiant located about 640 light-years from Earth in the constellation Orion, has an estimated radius between 700 and 900 times that of the Sunday. If Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Mars and possibly approach the asteroid belt. Despite this enormous size, Betelgeuse's mass is estimated to be only about 15 to 20 times that of the Sun, illustrating how low density these expanded stellar envelopes become. Another famous supergiant is Antares, located roughly 550 light-years away in the constellation Scorpius. Antares has a radius of approximately 680 solar radii and a luminosity around 60,000 times greater than the Sunday. Its outer atmosphere is diffuse, and material is continuously lost into surrounding space through powerful stellar winds. These winds transport heavy elements into the interstellar medium. Hypergiants are extremely rare and unstable, representing a brief phase in the life of the most massive stars. One of the largest measured examples is UY Scuti, located about 9,500 light-years away in the constellation Scutum. UY Scuti has an estimated radius of around 1,700 times that of the Sunday. If placed at the center of our solar system, its outer layers would extend beyond the orbit of Jupiter. Its mass is estimated to be 25 to 40 times that of the Sun, indicating that expansion reduces average density. Another hypergiant, VY Canis Majoris, located approximately 3,900 light-years away, has a radius estimated between 1,300 and 1,500 solar radii. Observations show that it is surrounded by clouds of expelled gas and dust, extending trillions of kilometers into space. Stars lack solid surfaces, and their outer layers gradually decrease in density, which can make precise size measurements challenging. The internal structure of these giant stars differs significantly from smaller stars like the Sunday. Their cores remain relatively compact, while their outer envelopes balloon outward due to intense radiation pressure. Temperatures at the surface of red supergiants can be as low as 3,000 degrees Celsius, cooler than the Sun's surface, which allows molecules and dust to form in their atmospheres. This combination of low surface temperature and vast radius contributes to their red appearance and immense luminosity. Even though they are cooler at the surface, their sheer size makes them some of the brightest stars in the galaxy. The lifespans of these massive stars are short compared to smaller stars. While the Sun will shine for about 10 billion years, a hypergiant may exist in its expanded form for only a few 100,000 years. Their high energy output consumes nuclear fuel at an accelerated rate, driving rapid evolution. Hypergiants are rare, with only a few dozen currently known in the Milky Way. Measuring the size of such stars requires advanced observational techniques. Interferometry allows astronomers to combine light from multiple telescopes to resolve stellar disks directly, even for stars hundreds or thousands of light-years away. Instruments such as the Very Large Telescope Interferometer have provided direct measurements of stars like Betelgeuse, revealing surface features such as convection cells that can be larger than Earth's orbit. These observations confirm that the largest stars are not smooth spheres, but dynamic, turbulent systems with constantly shifting surfaces. The scale of these stars also has implications for their surroundings. Supergiants and hypergiants emit intense ultraviolet radiation and powerful stellar winds that can compress nearby gas clouds, triggering new waves of star formation. At the same time, their radiation can strip atmospheres from nearby planets or prevent planets from forming at all. In star-forming regions, the presence of even a single massive giant star can alter the evolution of an entire stellar neighborhood, spanning dozens of light-years. Despite their large size, these stars are inherently unstable. The balance between gravity and radiation pressure becomes increasingly delicate as size increases. Pulsations, mass loss, and episodic eruptions are common. Eta Carinae, a hypergiant system about 7,500 light-years away, experienced an outburst in the 19th century that temporarily increased its brightness. During this event, it expelled material equivalent to several times the mass of the Sun, forming the Homunculus Nebula, which spans over a light-year in diameter. These stars can expand to sizes that precede collapse or explosion. Gravity drives their evolution toward endpoints such as supernovae. The expansion phase redistributes mass and alters the star's internal structure. The initial mass and structure influence the type of compact object that results after the explosion. Compared to the Sun, red supergiants and hypergiants have much larger radii. While the Sun may engulf Mercury in its red giant phase, stars, such as UY Scuti, have radii that extend well beyond the orbits of the inner planets. These stars exhibit how stellar radii increase significantly with initial mass and evolutionary phase, within the constraints of gravity and radiation pressure. Red giants, supergiants, and hypergiants experience changes in radius and luminosity over their lifetimes. These changes result from shifts in nuclear fusion and radiation pressure within the star, causing radii to increase by orders of magnitude compared to their initial size. After the expansion phase, red giants, supergiants, and hypergiants can collapse, forming compact stellar remnants such as white dwarfs, neutron stars, or black holes. These remnants are smaller in volume but contain significant mass and density, demonstrating the extremes of stellar evolution, stellar death, and the compact extremes. After witnessing the gargantuan expansion of red giants, supergiants, and hypergiants, the universe presents a remarkable contrast. Some of the most extreme and fascinating objects are tiny in size, yet immense in mass and gravitational influence. When stars exhaust their nuclear fuel, their life cycles can produce remnants so dense that a single teaspoon of matter would weigh billions of tons. White dwarfs, neutron stars, and the precursors to black holes illustrate a new level of cosmic scale, where volume shrinks dramatically, but influence, energy, and density reach unprecedented extremes. White dwarfs are remnants of low to medium mass stars, typically ranging from 0.8 to 8 solar masses. When these stars complete their hydrogen-burning phase, they shed their outer layers, forming intricate planetary nebulae. The remaining core, supported against gravity by electron degeneracy pressure, a quantum mechanical effect stabilizes into a white dwarf. Despite possessing a mass comparable to the Sun, approximately 1 × 1030 kilograms, white dwarfs have radii similar to Earth, around 7,000 kilometers. This produces densities up to 1,000,000 times greater than water. Sirius B, a companion to Sirius A, located about 8.6 light-years from Earth, has a mass of 1.02 solar masses, compressed into a volume smaller than our planet, making it a prime example of this extreme class of stars. The surface temperatures of white dwarfs are initially extremely high, often exceeding 100,000 degrees Celsius. Over billions of years, they gradually cool and fade into faint, dense stellar remnants. Their gravitational fields are significant, causing measurable gravitational redshift. In binary systems, accretion of matter from a companion star can trigger novae, where the white dwarf temporarily brightens thousands of times. For example, Nova Persei 1901 produced a temporary increase in brightness visible to the naked eye. Neutron stars take stellar compactness to an even more extreme level. These objects form from stars with initial masses between roughly 8 and 25 times that of the Sunday. Following a supernova explosion, the core collapses under gravity until neutrons are packed together tightly, with densities exceeding 4 × 1017 kilograms per cubic meter. Neutron stars typically measure only 10 to 20 kilometers in radius, yet contain between 1.4 and 2.3 solar masses. This incredible density compresses matter to conditions unattainable elsewhere in the universe, effectively forming a city-sized sphere with the mass of multiple suns. Some neutron stars are observed as pulsars, rotating rapidly and emitting beams of electromagnetic radiation. The Crab pulsar, located in the Crab Nebula approximately 6,500 light-years from Earth, rotates roughly 30 times per second. Millisecond pulsars, such as PSR J1748-2446 AD, spin more than 700 times per second. The radiation from these pulsars can be detected across the galaxy, allowing astronomers to study phenomena that combine extreme density, gravity, and magnetic fields. A neutron star's magnetic field is also immense, reaching values up to 10-11 teslas, far exceeding any magnetic fields found in planets or normal stars. The physics governing these objects introduces notable phenomena. Degeneracy pressure prevents complete collapse in white dwarfs and neutron stars, but only up to a point. For white dwarfs, the Chandrasekhar limit, approximately 1.44 solar masses, defines the maximum mass beyond which electron degeneracy cannot counteract gravity. Exceeding this limit can trigger a type Ia supernova, releasing as much energy in a few weeks as the Sun emits over billions of years. Neutron stars have a similar threshold. The Tolman-Oppenheimer Volkoff limit, estimated at around 2 to 3 solar masses, beyond which neutron degeneracy fails and the core collapses into a black hole. Observationally, compact stellar remnants are studied using multiple techniques. X-ray telescopes detect material accreting onto white dwarfs and neutron stars, where friction heats matter to millions of degrees. Gravitational wave observatories, such as LIGO and Virgo, have captured collisions between neutron stars, events that produce detectable space-time ripples and disperse heavy elements such as gold, platinum, and uranium into the galaxy. The GW170817 event, a neutron star merger observed in 2017, provided data on the production of heavy elements in such collisions. The evolution of massive stars that produce these remnants is rapid compared to lower-mass stars. Stars that end their lives as white dwarfs may take billions of years to reach this stage, whereas massive stars that produce neutron stars often live for only tens of millions of years before exploding as supernovae. White dwarfs vary in temperature as they cool over time, while neutron stars can rotate rapidly and possess strong magnetic fields. Some neutron stars, particularly magnetars, exhibit extreme conditions. Magnetars are neutron stars with magnetic fields about 10-14 to 10-15 teslas, roughly 1,000 times stronger than typical neutron stars. Their surface activity can produce giant flares detectable across the Milky Way, such as the 2004 flare from SGR 1806-20, which released more energy in a fraction of a second than the Sun emits in 100,000 years. Massive white dwarfs and neutron stars demonstrate the interplay between size and rotational dynamics. Neutron stars can rotate hundreds of times per second because their small radii reduce the moment of inertia. This rotational energy contributes to phenomena such as pulsar timing irregularities, precession, and glitches, which allow astronomers to probe internal structure and magnetic field evolution. Even small changes in rotation can release significant energy. White dwarfs, despite being Earth-sized, exert gravity hundreds of thousands of times stronger than Earth's. Neutron stars, measuring only a few kilometers across, distort spacetime significantly, bending light and slowing time in their vicinity. Observations of binary neutron star systems, where orbital periods change over time due to gravitational wave emission, provide direct evidence of these relativistic phenomena. The transition from neutron stars to black holes marks the extreme endpoint of stellar collapse. Once degeneracy pressures fail, mass compresses into a singularity surrounded by an event horizon, producing an object whose mass remains finite while its volume approaches zero. White dwarfs and neutron stars demonstrate how stellar evolution can produce objects with high density and strong gravitational influence. White dwarfs and neutron stars have high densities, strong gravitational fields, and significant energetic output. Accretion events, gravitational waves, magnetic activity, and element production occur in these remnants, illustrating physical processes on scales comparable to entire star systems. White dwarfs and neutron stars contribute to galactic environments. Material expelled during their formation adds to interstellar clouds. Binary interactions among these remnants can produce X-ray binaries, cataclysmic variables, and kilonovae, redistributing mass and energy across space. As compact objects vary in density and energetic behavior, massive stars can expand to sizes comparable to planetary orbits, whereas collapsed stellar cores, such as white dwarfs and neutron stars, are much smaller in volume but contain high mass and energy. These remnants are intermediate between ordinary stars and black holes, and extreme compression. Following the extreme densities of white dwarfs and neutron stars, the universe presents an even more radical endpoint of stellar evolution: black holes. Unlike any other objects we have examined, black holes combine enormous mass with a volume that approaches zero at the singularity, creating conditions where the laws of physics operate in extraordinary ways. They exemplify a unique form of largeness, not by physical dimensions, but by gravitational influence, energy interactions, and the curvature of space-time itself. Black holes demonstrate that in the cosmos, largest can also mean most extreme in effect. Stellar black holes form when massive stars, usually with initial masses greater than 25 solar masses, exhaust their nuclear fuel and undergo catastrophic core collapse. In these cases, electron and neutron degeneracy pressures are unable to resist gravity, causing the core to compress beyond the limits experienced by neutron stars. The resulting black hole can contain anywhere from 3 to tens of solar masses, all concentrated within a region defined by its event horizon. The event horizon marks the boundary beyond which nothing, not even light, can escape the black hole's gravitational pull. For a black hole with 10 times the Sun's mass, the Schwarzschild radius, the radius of its event horizon, is approximately 30 kilometers, roughly the size of a small city. Despite this seemingly small size, its gravitational influence extends far beyond the horizon, affecting surrounding stars, gas, and space itself. Supermassive black holes exist at the centers of most galaxies and contain millions to billions of solar masses. Sagittarius A star, the supermassive black hole at the center of the Milky Way, has a mass of approximately 4.3 million suns and a radius of roughly 12 million kilometers, nearly 1/10 the distance from Earth to the Sunday. Supermassive black holes exert gravitational forces that determine the orbits of stars near the galactic core. Observations show that nearly every large galaxy contains a supermassive black hole. Their masses often correlate with the properties of the galactic bulge, including the number of stars and overall luminosity. This relationship, known as the M-sigma relation, links black hole mass to stellar velocity dispersion in the host galaxy. For instance, M87 star, located in the galaxy Messier 87, has a mass of 5 billion solar masses. In 2019, the Event Horizon Telescope captured the first direct image of its shadow, revealing the circular silhouette of its event horizon against the bright surrounding emission, approximately 40 billion kilometers across. Intermediate mass black holes have masses between 100 and 100,000 solar masses. They have been detected through gravitational wave events and X-ray emissions. One example is HLX-1, located in the galaxy ESO 243-49, with an estimated mass of 20,000 solar masses. Some intermediate mass black holes may form from the merger of smaller black holes or the collapse of dense star clusters. Black holes warp spacetime so that nearby stars can experience extreme tidal forces. Material drawn toward the black hole can form an accretion disk, where friction heats matter to millions of degrees. This process generates X-ray and gamma-ray radiation, sometimes outshining entire galaxies. The quasar 3C273, powered by a supermassive black hole of about 900 million solar masses, emits energy equivalent to several trillion suns combined. Black holes produce observable phenomena beyond radiation. Binary black hole mergers generate gravitational waves, ripples in spacetime, first detected by LIGO in 2015. These waves carry information about the masses, spins, and orbits of colliding black holes. For example, the event GW150914 involved two stellar black holes of 36 and 29 solar masses merging to form a single black hole of 62 solar masses, with 3 solar masses converted directly into energy radiated as gravitational waves. The structure of black holes is defined by mass, radius, rotation, and charge. Rotating black holes, known as Kerr black holes, exhibit frame-dragging effects, twisting spacetime in the direction of rotation and accelerating orbiting matter. Charged black holes, or Reissner-Nordström black holes, demonstrate theoretical possibilities in which electrical charge influences gravitational structure, though these are likely rare. While stellar black holes can have densities comparable to neutron stars, supermassive black holes often have average densities lower than water due to their immense radii. The scale of a black hole can be described by its event horizon and gravitational influence. Observing black holes relies on indirect methods, since their defining property, the inability to emit light, prevents direct visual detection. Astronomers track the motion of stars orbiting invisible massive objects, as in the case of Sagittarius A star, or observe emissions from accretion disks in X-ray and radio wavelengths. Gravitational lensing, where the black hole's gravity bends light from background objects, provides another method for detecting distant black holes. Some black holes exhibit jets, narrow beams of high-energy particles emitted perpendicular to the accretion disk. These relativistic jets, often extending thousands of light-years, transport energy into surrounding space. The galaxy Centaurus A, powered by a central supermassive black hole, displays jets that extend over 10,000 light-years. Black holes affect galactic chemistry and evolution. Accretion events can trigger outflows that heat surrounding gas, suppressing star formation in the host galaxy, or compress gas to induce bursts of new star creation. Gravitational interactions may capture stars or star clusters, and galactic mergers can involve black holes colliding, producing gravitational waves and altering galactic structure. Time dilation occurs near black holes. According to general relativity, time slows near the event horizon compared to distant observers. Material falling toward the black hole appears to slow as it approaches the horizon, with photons increasingly redshifted. Observations of X-ray binaries and the inner edges of accretion disks confirm these relativistic effects. Black holes vary in mass and scale. Stellar black holes measure only tens of kilometers across, while supermassive black holes contain millions to billions of solar masses. Their gravitational influence affects surrounding stars and interstellar matter, and their accretion processes produce high-energy radiation detectable across vast distances. Solar systems as gravitational systems. After exploring the extraordinary extremes of black holes, the next level of cosmic scale shifts from objects of extreme density to collections of matter bound together by gravity. Solar systems are not merely groups of planets orbiting stars. They are dynamic gravitational domains that can stretch across billions of kilometers, incorporating planets, moons, asteroids, comets, and vast clouds of icy material at their edges. Understanding the size and structure of solar systems requires looking beyond the visible planets to the outer boundaries defined by gravity and stellar influence. The Sun, with a mass of 1.989 times 10^30 kilograms, dominates the gravitational center of the solar system, holding planets, dwarf planets, and countless smaller bodies in orbit. While Mercury orbits at an average distance of 58 million kilometers and Neptune at about 4.5 billion kilometers, the gravitational domain extends far beyond the visible planets. The Oort cloud, a hypothesized spherical shell of icy bodies, may reach distances up to 100,000 astronomical units, or nearly 2 light-years from the Sun. Although these objects are extremely sparse and mostly undetectable, they define the outer edge of the Sun's gravitational reach, making the solar system vastly larger than the orbits of the outer planets suggest. The Kuiper belt stretches from approximately 30 to 55 astronomical units and contains thousands of icy objects, including dwarf planets such as Pluto, Haumea, and Makemake. Pluto, at 2,377 kilometers in diameter, is a small component of this region, while the collective mass of Kuiper belt objects is estimated at 0.1 Earth masses, sufficient to influence planetary migration in the early solar system. Beyond the Kuiper belt lies the scattered disk, which extends farther and contains objects like Eris, measuring 2,326 kilometers in diameter and orbiting at distances exceeding 67 astronomical units. Asteroid belts further illustrate the diversity of solar system structure. The main asteroid belt between Mars and Jupiter contains millions of rocky bodies totaling roughly 4% of the Moon's mass. Some of these asteroids, like Ceres, Vesta, and Pallas, reach diameters of 900 to 940 kilometers, large enough to be classified as dwarf planets under certain definitions. Collisions within the asteroid belt have shaped the evolution of these bodies over billions of years, producing fragments and debris that occasionally cross paths with Earth. Even though the asteroid belt occupies a relatively small fraction of the solar system's volume, its cumulative mass and influence on planetary formation are substantial. Jupiter possesses at least 95 known moons, including Ganymede, the largest in the solar system, at 5,268 kilometers in diameter. Saturn has over 80 moons, including Titan, which is 5,150 kilometers across and has a dense atmosphere of nitrogen and methane. Moons create gravitational interactions, including tidal forces that affect planetary rotation and orbital stability. Comets, icy bodies originating from the outer regions, have long orbital periods that can take millions of years to complete. Comet Hale-Bopp, discovered in 1995, has a nucleus approximately 60 kilometers in diameter and an orbital period estimated at over 2,500 years. Comets from the Oort cloud, such as Comet C 2017 K2, can originate from distances greater than 20,000 astronomical units before entering the inner solar system. The heliosphere, a bubble of charged particles and magnetic fields generated by the Sun's solar wind, extends beyond the Kuiper belt to roughly 120 astronomical units. This boundary interacts with the interstellar medium, creating a shock front where the pressure of interstellar particles balances that of the solar wind. Voyager 1 and Voyager 2, the first human-made objects to leave the heliosphere, crossed this boundary in 2012 and 2018, providing direct measurements of the transition from solar to interstellar influence. During the early history of the solar system, giant planets like Jupiter and Saturn shifted positions, scattering smaller bodies into distant orbits. This process contributed to the formation of the Oort cloud and the scattered disk. Exoplanetary systems show additional configurations. Some stars host hot Jupiters, gas giants orbiting extremely close to their stars, while others have planets in eccentric, elongated orbits extending far beyond what is seen in the solar system. In binary and multiple star systems, gravitational forces from more than one star influence planetary orbits, creating stable zones and chaotic regions. For example, Kepler-16 is a binary system where a Saturn-sized planet orbits both stars. Circumbinary planets exist in regions influenced by multiple stellar masses. Disks like the one around HL Tauri, located 450 light-years away, extend hundreds of astronomical units and contain enough material to form multiple planetary systems. High-resolution imaging by ALMA has revealed rings and gaps within these disks, indicating planet formation in progress. The mass distribution within solar systems also contributes to their overall scale. In our solar system, Jupiter alone accounts for more than 99% of planetary mass. Its gravitational dominance shapes the orbits of other planets, asteroids, and even distant trans-Neptunian objects. Saturn, Uranus, and Neptune also contribute significantly, particularly in sculpting the Kuiper belt and influencing comet trajectories. The cumulative gravitational effect of all bodies determines the solar system's dynamic stability and defines the boundaries within which planets, moons, and smaller objects can maintain long-term orbits. As stars move through the galaxy, passing close to other stars or dense molecular clouds, their gravitational influence can perturb the outer regions of a solar system. Some comets may be ejected into interstellar space, while others may be nudged inward toward the inner planets. In addition to physical boundaries, solar systems can be defined by the regions where a star's gravity dominates over galactic tides. The Hill sphere, the region in which a star's gravity overpowers that of nearby stars, sets a practical outer limit for objects to remain gravitationally bound. For the Sun, this radius is roughly 1-2 light-years, encompassing the Oort cloud. The solar wind carries charged particles outward, interacting with planetary magnetospheres and the interplanetary medium. Spacecraft, such as the Parker Solar Probe, are measuring these processes, revealing how energy emitted by a star interacts with matter over billions of kilometers. Star clusters and stellar cities. After examining the vast gravitational domains of solar systems, the scale of cosmic organization expands dramatically when stars gather into communities. Star clusters are the stellar equivalents of cities, with hundreds to millions of stars bound together by gravity, interacting over vast distances, yet forming coherent, long-lived structures. Unlike individual stars or their planets, these clusters illustrate how collective mass and distribution define another level of cosmic largeness, producing gravitationally stable systems visible across thousands of light-years. There are two main types of star clusters: open clusters and globular clusters. Open clusters are relatively young, loose associations of stars, often containing a few dozen to a few thousand members. They are typically found within the galactic disk, where ongoing star formation occurs. One of the best-known examples is the Pleiades, located roughly 444 light-years away in the constellation Taurus. The Pleiades contains over 1,000 stars, most of which are hot, blue, B-type stars between 10 and 100 million years old. Despite their youthful energy, open clusters are fragile. Gravitational interactions with nearby stars and molecular clouds gradually disperse their members over hundreds of millions of years. The spatial dimensions of open clusters vary significantly. The Hyades, another prominent cluster, is located about 153 light-years away in Taurus and spans roughly 20 light-years across. Its 400 or more identified members include stars such as Aldebaran, which appears within the cluster from Earth's perspective, but is actually a foreground object. Open clusters provide valuable insight into stellar evolution, as stars in these groups share a common age and chemical composition, allowing astronomers to study the effects of mass and metallicity on stellar life cycles. In contrast, globular clusters are ancient, densely packed systems containing hundreds of thousands to millions of stars. These clusters orbit galactic halos rather than residing in the disk, and can survive for billions of years due to their tightly bound gravitational structure. M13, the Great Hercules Cluster, is one of the brightest globular clusters visible from Earth, situated about 22,200 light-years away, and containing roughly 300,000 stars within a radius of 145 light-years. Omega Centauri, the largest known globular cluster in the Milky Way, contains over 10 million stars and spans nearly 150 light-years in diameter. The population density within these clusters is extraordinary. In the core regions of globular clusters, stars can be separated by only a fraction of a light-year, compared to several light-years between neighboring stars in the Sun's vicinity. These close proximities lead to frequent stellar interactions, including binary star formation, tidal stripping, and even collisions between stars. For instance, the cluster M15 exhibits a dense core where collisions have likely formed exotic objects, such as blue stragglers stars, that appear younger and hotter than the majority of cluster members. Open and globular clusters also display diversity in stellar content. While open clusters are dominated by young, massive stars, globular clusters contain primarily old, low-mass stars, with ages ranging from 10 to 13 billion years. The chemical abundances in globular cluster stars vary, with some clusters, such as 47 Tucanae, containing multiple stellar populations with slightly different ages and compositions, indicating that star formation in clusters can occur in successive waves rather than a single burst. Stellar clusters are collections of stars exhibiting a range of gravitational dynamics. The internal velocity dispersion of stars within clusters typically ranges from a few kilometers per second in open clusters to 10-20 kilometers per second in globular clusters. These motions influence cluster morphology, core collapse rates, and long-term stability. In addition, tidal forces from the host galaxy strip stars from clusters over time, forming extended streams of stars that can stretch across thousands of light-years. The Sagittarius stream, for example, contains stars torn from the Sagittarius dwarf elliptical galaxy and its associated clusters as it merges with the Milky Way. Clusters can also contain exceptional stellar objects. Neutron stars and pulsars are commonly found in globular clusters, likely formed from the collapse of massive stars in the cluster's early history. Terzan 5, a globular cluster about 19,000 light-years away, contains at least 37 known pulsars, the largest number found in any cluster to date. The dense environment favors binary interactions that can spin up neutron stars, producing millisecond pulsars. These pulsars serve as precise clocks, enabling studies of cluster dynamics, gravitational potential, and even relativistic effects in dense stellar environments. Binary star systems are abundant in clusters, with estimates suggesting that 10–50% of stars in globular clusters exist in binaries. These systems drive complex interactions, including mass transfer, accretion phenomena, and stellar mergers. X-ray binaries, in which a neutron star or black hole accretes material from a companion, are frequently observed in clusters. The size and scale of clusters extend beyond the cluster itself. Stars ejected by dynamical interactions can travel significant distances, forming halo populations or contributing to tidal streams. The Palomar clusters, discovered in the 1,950 seconds, are faint globular clusters in the Milky Way halo, often observed at distances exceeding 50,000 light-years from the galactic center. Clusters also exist in other galaxies, often on an even larger scale. The Large Magellanic Cloud hosts several massive clusters, such as NGC 1850, which contains tens of thousands of stars within a radius of 25 light-years. Starburst galaxies, like M82, produce dense clusters that may serve as precursors to globular clusters, containing hundreds of thousands of stars formed in a single, intense episode. The study of clusters provides information about the evolution of galaxies. The distribution, mass, and age of globular clusters serve as traces of galactic formation and mergers. For example, the Milky Way contains over 150 known globular clusters, with spatial distributions revealing interactions with satellite galaxies and accretion events. The chemical composition of cluster stars records enrichment of interstellar matter over billions of years. In terms of size, the largest stellar clusters span hundreds of light-years in diameter and contain millions of stars. Their gravitational cohesion allows them to survive long after their formation. Open clusters, by contrast, are smaller and more fragile, with diameters of tens of light-years and lifespans measured in hundreds of millions of years. Star clusters vary in population, spatial extent, and gravitational influence. Black holes exert strong gravitational pull, whereas clusters contain hundreds to millions of stars bound together. Observations of clusters provide data on stellar interactions, evolution, and high-energy phenomena, as well as their distribution within host galaxies. Galaxies' islands of hundreds of billions. Having explored the dense gatherings of stars within clusters, the cosmic scale expands dramatically when these clusters coalesce into galaxies, sprawling islands of hundreds of billions of stars bound by gravity. Galaxies represent the next level of structure in the universe, vast systems not only containing stars, but also gas, dust, dark matter, and sometimes central supermassive black holes. Their immense sizes and diverse forms demonstrate how matter organizes on scales far beyond individual stellar cities. Galaxies come in a variety of shapes and structures. Spiral galaxies, like the Milky Way, are characterized by a flat, rotating disk of stars, with distinct spiral arms, a central bulge containing older stars, and a surrounding halo of globular clusters and dark matter. The Milky Way is approximately 100,000 light-years in diameter and contains an estimated 200 to 400 billion stars. Its spiral arms, such as the Perseus and Scutum Centaurus arms, contain dense regions of star formation where gas and dust coalesce to form new stars. Elliptical galaxies, in contrast, are more spheroidal and can range from a few thousand to over 1 million light-years in diameter. These galaxies contain older, low-mass stars and relatively little interstellar gas, meaning star formation occurs at a much slower rate than in spirals. Messier 87, a giant elliptical galaxy located about 53 million light-years away in the Virgo cluster, is roughly 120,000 light-years across and contains trillions of stars. Its central supermassive black hole, M87 star, is one of the most massive known, with a mass of 6.5 billion suns, influencing the dynamics of the galaxy's inner region and powering a relativistic jet extending over 5,000 light-years. Irregular galaxies, lacking a distinct shape, provide another dimension of diversity. These galaxies often result from gravitational interactions or collisions with other galaxies, leading to chaotic distributions of stars, gas, and dust. The Large Magellanic Cloud, a satellite of the Milky Way located about 163,000 light-years away, is an example of an irregular galaxy with active star formation regions, such as 30 Doradus, also known as the Tarantula Nebula. This nebula alone spans 650 light-years and contains some of the most massive stars ever observed, exceeding 200 solar masses. Galaxy sizes vary enormously. Dwarf galaxies, like the Fornax dwarf, contain a few billion stars and span only a few thousand light-years, while giant galaxies, like IC 1101, located over a billion light-years away, contain over 100 trillion stars and extend more than 6 million light-years across. The Milky Way has a total mass, including dark matter, estimated at 1.5 trillion solar masses, while supergiant galaxies may reach 10 or more times that value. The distribution of stars and matter within galaxies is far from uniform. In spiral galaxies, stars in the central bulge are densely packed, with typical densities reaching several hundred stars per cubic parsec. In the disk, stars are more sparsely distributed, separated by several light-years on average, while the halo contains stars separated by tens of thousands of light-years. Elliptical galaxies, though less structured, can have dense cores, with millions of stars per cubic parsec. This concentration impacts gravitational dynamics, stellar interactions, and the motion of satellite systems such as globular clusters or dwarf galaxies. Galaxies are not isolated. Many exist in groups and clusters bound by gravity, where interactions and collisions affect their structures. The local group, containing over 50 galaxies, including the Milky Way and Andromeda, spans roughly 10 million light-years. Tidal forces in these environments can distort galactic shapes, strip stars, and trigger bursts of star formation. Andromeda, the largest galaxy in the local group, contains about 1 trillion stars and has a diameter of roughly 220,000 light-years. Dark matter significantly contributes to galactic mass. Observations show that visible matter accounts for only a small fraction of the total mass required to explain rotational curves and gravitational lensing effects. In the Milky Way, stars, gas, and dust contribute roughly 60 billion solar masses, while dark matter may account for over 1 trillion solar masses. This invisible component extends beyond the visible disk, forming a halo that can reach several 100,000 light-years. Galaxies host diverse stellar populations and phenomena. Globular clusters orbit galaxies, forming dense satellite systems, while open clusters populate disks and spiral arms. Supernovae, both type Ia and core collapse varieties, occur throughout galaxies, enriching the interstellar medium with heavy elements. Massive stars, such as those in the Tarantula Nebula, explode in supernovae, releasing more energy in seconds than the Sun emits over its entire lifetime. Gas and dust clouds in galaxies stretch hundreds to thousands of light-years and provide material for star and planet formation. Molecular clouds like Orion, 24 light-years across and containing roughly 200,000 solar masses, are examples of galactic substructures. Spiral density waves in galaxy disks compress gas to trigger star formation along spiral arms, while supernova shock waves propagate energy across regions, affecting stellar populations. Galaxies can contain supermassive black holes at their centers, affecting both local and global dynamics. These black holes influence the motion of stars in the central bulge, drive relativistic jets, and regulate star formation through energetic outflows. In active galactic nuclei, accretion onto the black hole releases tremendous energy, sometimes outshining the combined light of all the galaxy's stars. Quasars, such as 3C 273 inches the constellation Virgo, emit luminosities equivalent to hundreds of billions of suns. The formation of galaxies is a hierarchical process. Smaller structures merge to form larger ones, as seen in simulations of galaxy evolution. Dwarf galaxies coalesce into spirals or ellipticals. Clusters of galaxies assemble into larger collections, and superclusters trace the cosmic web of matter. Observations of high redshift galaxies indicate that even in the early universe, galaxies contained billions of stars. Galaxies vary in size and mass, with their stellar populations, dark matter halos, and energetic processes contributing to their overall structure. Star clusters contain thousands to millions of stars within tens to hundreds of light years, while galaxies extend across tens of thousands to millions of light years, containing hundreds of billions of stars and large reservoirs of gas and dark matter. The dark matter halo of a galaxy can extend well beyond the visible disk, affecting the orbits of stars and satellite systems, galactic halos, and dark matter mass. Following our exploration of galaxies as sprawling islands of hundreds of billions of stars, we now turn to the hidden yet dominant structures that define their true scale: galactic halos and the invisible mass within them. While the luminous stars, gas, and dust often capture attention, they represent only a fraction of a galaxy's total mass. Surrounding every galaxy is an extended, nearly spherical halo composed largely of dark matter, a mysterious substance that exerts gravitational influence without emitting or absorbing light. These halos can stretch several 100,000 light-years from the galactic center, vastly exceeding the visible boundaries of stars and gas. The concept of a galactic halo emerged from observations of rotation curves in spiral galaxies. In the 1,970 seconds, astronomers like Vera Rubin and Kent Ford measured the orbital speeds of stars at various distances from galactic centers and found that stars far from the center moved much faster than predicted based on visible matter alone. In the Milky Way, stars at distances of 50,000 light-years orbit at speeds of approximately 220 kilometers per second, a velocity maintained well beyond the edge of the visible disk. This discrepancy indicated the presence of an unseen mass extending far beyond the luminous component of the galaxy. Dark matter dominates these halos. In the Milky Way, estimates suggest that luminous stars and gas account for only about 6% of the total mass, while dark matter comprises roughly 94%. This dark matter halo likely extends at least 300,000 light-years from the galactic center, far beyond the orbit of the outermost dwarf galaxies. Similar structures are observed around other galaxies, with mass-to-light ratios sometimes exceeding 100:1. This invisible mass not only defines the galaxy's total gravitational potential, but also dictates the motion of satellite galaxies, globular clusters, and intergalactic gas streams. Galactic halos are not composed solely of dark matter. They also contain hot, diffuse gas detectable in X-ray wavelengths. In the Milky Way, this circumgalactic medium extends for hundreds of thousands of light-years, with temperatures reaching millions of degrees Kelvin. Observations with the Chandra X-ray Observatory and XMM Newton have revealed filamentary structures of this hot gas, interacting with infalling dwarf galaxies and shaping star formation in the galactic disk. The mass of this gas is estimated to be comparable to that of all the stars in the Milky Way, emphasizing that even visible baryonic matter extends far beyond the familiar disk. Halo stars form another important component. Unlike disk stars that move in orderly orbits around the galactic center, halo stars travel in more random elliptical paths. These stars are typically older and metal-poor, reflecting the early stages of galaxy formation. The globular clusters discussed previously often reside within halos, orbiting hundreds to thousands of light-years above the galactic plane. For example, Omega Centauri, the largest globular cluster in the Milky Way, orbits the halo at distances ranging from 15,000 to 20,000 light-years from the center. Satellite galaxies provide additional evidence of halo largeness. The Milky Way hosts over 50 known satellites, including the Large and Small Magellanic Clouds, Leo YN2, and ultra-faint dwarfs, such as Segway 1. These satellites orbit within the gravitational influence of the Milky Way's dark matter halo, with some following highly elliptical trajectories extending hundreds of thousands of light-years from the galactic center. Interactions between satellites and the halo can produce tidal streams, such as the Sagittarius stream, which stretches over 100,000 light-years across the sky. These streams trace the galaxy's gravitational footprint far beyond the visible stellar disk. Halo size also varies across galaxy types. Giant ellipticals often have enormous halos that dominate their local group environment. Messier 87, the massive elliptical at the center of the Virgo cluster, possesses a dark matter halo extending over 1 million light-years. Dwarf galaxies, in contrast, have much smaller halos, yet even they are disproportionately large relative to their stellar content. Studies of ultra-faint dwarf galaxies reveal that their stars contribute only a few thousand solar masses, while their dark matter halo may exceed 1 million solar masses. Gravitational lensing has been crucial for mapping these halos. Massive galaxies bend the light from more distant objects, creating arcs and multiple images. Observations of lensing in systems such as the Bullet cluster have confirmed that most mass is not associated with luminous matter. These measurements allow astronomers to infer the distribution and density of dark matter, revealing halos that extend well beyond visible boundaries and dominate the dynamics of entire galactic neighborhoods. Halos also shape the motion of stars within galaxies. In spiral galaxies, the dark matter halo contributes to the flat rotation curves observed far from the center. In ellipticals, halo mass influences the velocity dispersion of stars in the spheroidal component. Satellite systems, globular clusters, and tidal debris respond to the combined gravitational potential of luminous and dark matter. Galaxy mergers provide further insight into halo structure. When galaxies collide, their dark matter halos interact first, guiding the trajectories of the luminous components. In clusters of galaxies, individual halos may overlap, forming larger potential wells that bind hundreds of galaxies together. For example, the Coma cluster contains over 1,000 galaxies embedded in a shared dark matter halo that stretches over 20 million light-years. Observations of high redshift galaxies suggest that halos form early in the universe. Dark matter collapsed into dense regions known as halos within the first billion years after the Big Bang, providing the scaffolding for baryonic matter to coalesce into stars and galaxies. Modern surveys using the Hubble Space Telescope and the Atacama Large Millimeter Submillimeter Array have identified galaxies at redshifts greater than 10, indicating that halo-driven structure formation was already underway within 500 million years of the Big Bang. The combination of dark matter, diffuse gas, halo stars, globular clusters, and satellite galaxies reveals that galactic halos extend far beyond the visible disks, encompassing distances and masses orders of magnitude larger than the luminous components. While the spiral arms of a galaxy, or the bright core, may measure tens of thousands of light-years, the halo can stretch hundreds of thousands, sometimes millions, of light-years. Galactic halos interact with neighboring halos, influence the formation of galaxy groups and clusters, and contribute to the large-scale cosmic web. The mass in halos affects how galaxies move relative to one another, and how filaments of matter form throughout space. Halos and their mass influence galaxy dynamics, interactions, and the behavior of surrounding structures. Hidden components of galaxies contribute to the formation of galaxy clusters and superclusters, galaxy groups and clusters. Moving beyond individual galaxies and their extensive halos, the universe organizes matter on an even grander scale through galaxy groups and clusters. These systems contain dozens to thousands of galaxies bound together by gravity, forming the building blocks of the large-scale cosmic structure. Unlike isolated galaxies, groups and clusters reveal how galaxies interact, merge, and influence one another across distances of millions of light-years. providing a new perspective on what it means to be large in the cosmos. Galaxy groups are the smallest gravitationally bound collections, typically containing a few dozen galaxies. The local group, which includes the Milky Way, Andromeda, and roughly 50 other smaller galaxies, spans about 10 million light-years. Within this group, the Milky Way and Andromeda dominate in mass and size, each hosting hundreds of billions of stars and extensive halos of dark matter, while smaller dwarf galaxies like Leo I and the Canes Venatici I dwarf orbit them. Groups provide a laboratory for understanding gravitational interactions, as tidal forces can strip stars from satellites, produce tidal streams, and trigger bursts of star formation within affected galaxies. The Sagittarius stream, for instance, stretches over 100,000 light-years and originates from the ongoing disruption of the Sagittarius dwarf galaxy by the Milky Way. In addition, the discovery of ultra-faint dwarf galaxies, such as Segway 1 and Boots I, orbiting the Milky Way, demonstrates that even tiny galaxies can contribute to the overall mass and dynamical complexity of a group. Galaxy clusters are far larger and more massive, often containing hundreds or thousands of galaxies. These clusters can span several million light-years across and possess total masses exceeding 10-15 solar masses. The Coma cluster, located about 321 million light-years away, contains over 1,000 identified galaxies, including massive ellipticals like NGC 4874 and NGC 4889, each containing trillions of stars. Clusters are dominated not by visible galaxies alone, but by an enormous amount of dark matter, which accounts for roughly 80–90% of the cluster's total mass, creating a gravitational well that holds the entire system together. Many clusters also contain smaller groups that have been accreted over time, adding to their complexity. Intergalactic gas within clusters is another critical component. This hot plasma, known as the intracluster medium, can reach temperatures of tens of millions of degrees Kelvin and emits X-rays detectable by observatories such as Chandra and XMM Newton. In the Coma cluster, the mass of this gas alone is comparable to, or even exceeds, the combined mass of all the galaxies within the cluster. The density of the intracluster medium varies, with cores often having denser, hotter gas due to gravitational compression and cooling flows. Observations of clusters such as Perseus and Abell 2029 show that the gas is enriched with heavy elements like iron, silicon, and oxygen, produced by countless generations of supernovae. Clusters can also be classified by morphology. Regular or relaxed clusters, such as Abell 1689, show spherical symmetry and a dense, centrally concentrated core. Irregular clusters, on the other hand, often form from the collision of smaller clusters, producing elongated or disturbed shapes. The Bullet cluster is a notable example, where two clusters collided at approximately 3,000 kilometers per second. Observations of gravitational lensing in this system revealed the separation of dark matter from baryonic gas, providing some of the clearest evidence for dark matter's existence. In addition to collisions, ram pressure stripping occurs within clusters, where galaxies moving through dense intracluster gas lose their own gas reservoirs. This process has been observed in galaxies in the Virgo cluster, where tails of stripped gas stretch tens of thousands of light-years, visually demonstrating the immense forces at play. Clusters are home to a wide diversity of galaxy types. Elliptical galaxies often dominate the dense cores of clusters, while spiral and irregular galaxies are more common in the outskirts. The Virgo cluster, the nearest large cluster to the local group at about 53 million light-years away, contains roughly 1,300 member galaxies. Its core is densely populated with giant ellipticals such as M87, while the periphery hosts smaller spirals like M90 and M100. Interactions, mergers, and tidal forces affect morphology, star formation rates, and gas content. Many clusters also contain low-surface brightness galaxies, which are diffuse and difficult to detect, but can extend across tens of thousands of light-years. The gravitational influence of clusters extends well beyond their visible boundaries. The dark matter halos of member galaxies and the collective cluster halo generate a gravitational field that governs the motion of galaxies across millions of light-years. Typical velocities of galaxies within massive clusters reach 1,000 to 2,000 kilometers per second. These high velocities prevent clusters from dispersing, despite the vast distances between individual galaxies. Observing galaxy motions within clusters enables astronomers to estimate the total cluster mass, often revealing that dark matter far outweighs luminous matter. Clusters like Abell 2744, also called Pandora's cluster, contain extreme numbers of interacting galaxies, with gravitational interactions creating multiple tidal features, arcs, and streams. Clusters also host spectacular high-energy phenomena. Galaxy interactions frequently trigger starbursts, active galactic nuclei, and supernovae. In the Perseus cluster, about 75% of galaxies exhibit enhanced star formation or active cores due to interactions within the dense environment. Central galaxies in massive clusters often harbor supermassive black holes, sometimes exceeding 10 billion solar masses. These black holes can drive relativistic jets that extend hundreds of thousands of light-years, influencing the temperature and distribution of the intracluster medium. Observations of radio halos in clusters, such as the Coma cluster, show diffuse synchrotron emission produced by relativistic electrons interacting with magnetic fields, adding another layer to cluster-scale phenomena. Satellite galaxies and tidal debris further highlight the scale of clusters. Streams of stars and stripped gas can stretch across hundreds of thousands of light-years, connecting galaxies within the cluster. The Virgo cluster contains numerous such streams, remnants of past interactions that continue to shape the cluster's structure. Similarly, the Coma cluster exhibits extended halos of intracluster stars, collectively forming an invisible population that adds to the system's total luminosity and mass. Clusters are not isolated. They themselves group into larger structures. Superclusters, like the Laniakea supercluster, encompass multiple clusters and groups, stretching over hundreds of millions of light-years. The local group, for instance, is part of the Virgo supercluster, which contains thousands of galaxies bound by a complex network of dark matter and gravitational interactions. Observations of galaxy distributions in surveys such as the Sloan Digital Sky Survey show that clusters are connected by filaments of galaxies and gas, forming the backbone of the cosmic web. Clusters provide a window into cosmic history. Many are ancient, with formation ages exceeding 10 billion years. Their constituent galaxies, intracluster medium, and dark matter serve as traces of evolution over time. Observing chemical abundances in cluster gas reveals enrichment from generations of supernovae, while the morphology-density relation indicates how interactions in dense environments alter galaxy shapes and star formation. Mergers between clusters can release kinetic energy exceeding 1063 ergs, comparable to the energy output of billions of supernovae. Fossil groups are dominated by a single giant elliptical and surrounded by X-ray emitting gas. A single cluster can span millions of light-years and contain mass equivalent to millions of billions of suns. Their gravitational influence extends further, affecting the motion of nearby groups and filaments. Clusters form from the collective organization of galaxies, gas, and dark matter and contribute to supercluster-scale structures, superclusters, and cosmic architecture. Beyond galaxy clusters, the universe organizes matter on a scale that is almost unimaginable. Superclusters. These structures represent vast networks of galaxy groups and clusters, stretching over hundreds of millions of light-years and containing masses equivalent to quadrillions of suns. Unlike clusters, which are gravitationally bound and relatively compact, superclusters are sprawling and loosely bound, their gravitational ties weaker but still significant over cosmic distances. Studying superclusters reveals how the universe arranges itself on the largest intermediate scales and provides insight into the immense cosmic architecture that connects clusters into an even grander system. One of the most well-known superclusters is Laniakea, the cosmic home of our Milky Way. This supercluster spans roughly 520 million light-years in diameter and contains an estimated 100,000 galaxies. The Milky Way, along with the local group, resides on the outskirts of Laniakea, embedded within a gravitational basin called the local void. Laniakea's discovery relied on mapping the velocities of galaxies and their peculiar motions, revealing the large-scale flow of matter toward the gravitational center known as the Great Attractor. The total mass of Laniakea, including dark matter, is estimated at about 10-17 solar masses, highlighting how the combination of visible and invisible matter defines cosmic structures at supercluster scales. Superclusters vary widely in shape and density. Some are elongated, filament-like structures, while others resemble flattened sheets or walls. The Shapley supercluster, one of the most massive known, lies about 650 million light-years away and contains over 8,000 galaxies, most of them concentrated in several dense clusters. The core of Shapley alone has a mass exceeding 10-16 solar masses. The sheer gravitational influence of such superclusters affects the motion of surrounding clusters and groups, bending the paths of galaxies over distances of hundreds of millions of light-years. Observations show that clusters within superclusters tend to align along filamentary structures, suggesting that matter preferentially flows along these cosmic highways during the universe's formation. Filaments connecting superclusters are among the largest structures in the observable universe. These filaments, composed of galaxies, gas, and dark matter, can stretch hundreds of millions of light-years in length, while remaining only tens of millions of light-years thick. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, spans roughly 1.4 billion light-years, making it one of the most massive known filamentary structures. Within these filaments, galaxy densities vary, with clusters concentrated at filament intersections and smaller groups populating the elongated stretches between them. Galaxies form groups cluster into larger clusters, clusters assemble into superclusters, and superclusters interconnect through filaments. The Horologium Reticulum supercluster, located approximately 700 million light-years away, contains over 20 massive clusters and hundreds of smaller groups, with intercluster gas detectable through X-ray emissions, highlighting the presence of hot plasma spread across these vast distances. Dark matter within these superclusters dominates the gravitational field, shaping the motion of galaxies and clusters while remaining invisible to direct observation. Superclusters exhibit dynamic processes on scales beyond individual galaxies or clusters. Mergers of clusters within superclusters generate shocks in the intracluster medium, heating gas to tens of millions of degrees. In addition, gravitational interactions can strip gas from galaxies, forming massive streams of intergalactic material that feeds star formation in neighboring galaxies. Observations of superclusters, like the Corona Borealis supercluster, reveal that galaxy velocities within the structure can reach 1,500 kilometers per second, indicating intense gravitational interactions over hundreds of millions of years. Unlike clusters, superclusters are often not fully gravitationally bound and may be slowly drifting apart as the universe expands. Within them, smaller structures like groups and clusters remain bound, creating islands of density within a larger, more tenuous framework. Superclusters also vary in composition. Some are dominated by rich clusters with massive elliptical galaxies, while others contain a higher proportion of spiral and irregular galaxies. The Perseus-Pisces supercluster, located about 250 million light-years away, is a filamentary chain stretching over 400 million light-years and containing dozens of clusters. Within Perseus-Pisces, the Abell 426 cluster dominates the central region with thousands of member galaxies, and X-ray observations reveal a hot intracluster medium that contributes a significant fraction of the supercluster's baryonic mass. The discovery of superclusters relies heavily on redshift surveys, which measure the distances and velocities of galaxies. Large-scale surveys like the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey have revealed hundreds of superclusters within the observable universe. These surveys demonstrate that galaxies are not randomly distributed. Instead, they occupy a cosmic web where dense regions of superclusters and clusters are connected by filaments, interspersed with enormous voids spanning tens of millions of light-years with very few galaxies. Superclusters also serve as a testing ground for understanding dark matter and dark energy. The distribution and motion of galaxies within these structures provide constraints on the universe's total mass, the behavior of dark matter, and the influence of dark energy on cosmic expansion. In the Shapley supercluster, for example, observations of galaxy velocities indicate that visible matter accounts for only a fraction of the total mass, while dark matter dominates the gravitational potential, guiding the flow of galaxies and clusters. A single supercluster can contain masses equivalent to hundreds of millions of billions of suns, stretch hundreds of millions of light-years, and influence the motion of thousands of galaxies. These structures are dynamic, evolving systems that continue to interact and grow over billions of years. Observations indicate that superclusters form part of a connected network spanning large volumes of the observable universe. In addition to gravitational interactions, superclusters also reveal the interplay of cosmic evolution and energy distribution. Star formation rates vary across these structures, with denser clusters tending to suppress star formation in their galaxies, while filamentary regions show more active star formation. Radio observations of superclusters detect synchrotron emission produced by cosmic rays interacting with magnetic fields over millions of light-years. Galaxies, clusters, and groups assemble into massive networks within superclusters, illustrating the hierarchical organization of cosmic matter. From the Laniakea supercluster to the Perseus-Pisces chain, these structures occupy billions of light-years and form part of the large-scale cosmic web. The cosmic web, beyond superclusters, lies the largest and most intricate structure in the observable universe. The cosmic web. This immense network of filaments, walls, and voids forms a complex framework of matter that stretches across billions of light-years, connecting superclusters and shaping the universe's large-scale architecture. While individual galaxies, clusters, and superclusters reveal extraordinary mass and size, the cosmic web demonstrates a level of largeness that surpasses comprehension, illustrating how matter organizes itself on the grandest scales. Observations of the cosmic web rely on extensive redshift surveys, gravitational lensing, X-ray mapping, and computer simulations tracing both luminous matter and the invisible dark matter that dominates the cosmos. The most striking components of the cosmic web are filaments, elongated, thread-like structures of galaxies, gas, and dark matter extending over hundreds of millions of light-years. Filaments act as highways of matter, channeling galaxies and clusters toward dense nodes where superclusters form. A single filament can host thousands of galaxies, each containing billions of stars, along with hot, diffuse gas and dark matter. The Sloan Digital Sky Survey has mapped numerous filaments, including the CFA-2 Great Wall, which spans roughly 500 million light-years and contains countless galaxies and galaxy clusters. Filaments are not uniform. Their widths typically range from 10 to 50 million light-years, and the density of galaxies along a filament can vary significantly, with clusters concentrated at intersections while smaller groups populate the stretches in between. Interwoven with filaments are vast voids, regions of space with very few galaxies. These empty regions can stretch tens to hundreds of millions of light-years across, with the Botas void often referred to as the Great Nothing, spanning approximately 330 million light-years. Despite their emptiness, voids play a critical role in shaping the universe's large-scale structure. The gravitational pull of denser filaments and clusters draws matter out of voids, accelerating galaxies toward these dense regions. Voids can also affect galaxy formation, as galaxies within low-density regions tend to retain more gas and exhibit higher star formation rates than those in dense filaments, providing insight into how the environment influences galactic evolution. Walls or sheets are additional defining features of the cosmic web. These planar structures are formed where multiple filaments intersect, creating broad planes of galaxies and clusters. The Sloan Great Wall, discovered in 2003, extends more than 1.4 billion light-years and contains numerous superclusters aligned along its expanse. These walls guide the motion of galaxies over vast distances and often contain dense clusters and groups along their lengths. Dark matter forms the invisible backbone of the cosmic web, while galaxies, clusters, and filaments provide luminous tracers. Roughly 85% of the universe's total matter exists as dark matter. Its gravitational influence shapes the distribution of visible matter, drawing gas and galaxies into dense nodes and creating the characteristic web-like pattern. Observations using gravitational lensing, such as around the Abell 1689 cluster, have enabled astronomers to map dark matter along filaments, confirming that these invisible structures extend far beyond the reach of ordinary matter. Filaments are dynamic environments where galaxies interact and evolve. Galaxies flowing along filaments often collide at filament intersections, triggering starbursts and feeding supermassive black holes. The Hydra Centaurus supercluster filament, about 150 million light-years away, exemplifies this activity. Galaxies along the filament display tidal interactions, warp disks, and evidence of gas stripping, while the filament's nodes contain massive ellipticals and active galactic nuclei emitting strong X-ray and radio signals. Hot plasma within these filaments, with temperatures exceeding 1 million degrees Kelvin, slowly flows along the structures and contributes to the intracluster medium of the clusters that form at filament intersections. Large-scale simulations, such as the Millennium and Illustris simulations, suggest that the cosmic web formed from minute quantum fluctuations in the early universe, amplified by gravitational forces over billions of years. These density variations led to the formation of the first dark matter halos, which attracted gas and generated the earliest galaxies. Over time, galaxies assembled into groups, clusters, superclusters, and eventually the filaments and walls observed today. Observations of distant galaxies at high redshifts show that the web's filamentary structure existed when the universe was less than half its current age, indicating that these patterns emerged early in cosmic history. The gravitational interactions within the cosmic web are immense. Filament intersections are regions of extremely high density, where clusters merge and release energy equivalent to billions of supernovae. The Laniakea supercluster, encompassing the Milky Way, contains hundreds of thousands of galaxies flowing toward the Great Attractor, a dense gravitational node influencing motion over hundreds of millions of light-years. Mapping the cosmic web requires precise measurements of galaxy positions, redshifts, and velocities. Surveys, such as the 2DF Galaxy Redshift Survey, the Sloan Digital Sky Survey, and the Cosmic Flows Project have mapped thousands of filaments, revealing a complex three-dimensional network of walls, clusters, and voids. In addition, gravitational lensing studies have allowed astronomers to detect dark matter filaments connecting clusters, confirming that these invisible structures guide galaxy motion across enormous distances. Filaments can span hundreds of millions of light-years, connecting multiple superclusters into continuous networks. Within a single filament, the combined mass of galaxies, dark matter, and intrafilament gas can exceed that of several galaxy clusters combined. Voids, while nearly empty, can extend across hundreds of millions of light-years, showing the contrast between densely packed structures and the vast empty spaces in the web. Filaments grow as matter flows into dense nodes, clusters merge to form larger superclusters, and voids expand as galaxies migrate toward filaments. Observations of high redshift regions show the web already forming more than 10 billion years ago. Energetic activity, such as the inflow of hot gas, the acceleration of cosmic rays, and the jets from supermassive black holes, occurs along filaments and at intersections. Magnetic fields within the cosmic web also contribute to its complexity. Measurements of radio emissions from filaments, such as those in the Coma supercluster region, indicate the presence of large-scale magnetic fields extending over millions of light-years. These fields interact with cosmic rays, producing diffuse radio halos and affecting galaxy evolution by influencing the motion of gas within filaments. Additionally, shocks from colliding clusters within filaments can heat gas to tens of millions of degrees, contributing to the intracluster and interfilament medium. Ultimately, the cosmic web binds superclusters, clusters, and groups into a continuous network spanning billions of light-years. Within this network, individual filaments and nodes contain large amounts of mass, both visible and invisible, while voids form low-density regions, the largest known structures ever observed. When examining the universe on the grandest scales, astronomers have identified structures so immense that they redefine our understanding of large. These are the record-holding cosmic formations, massive walls, filaments, and superstructures composed of billions of galaxies stretching across hundreds of millions to billions of light-years. Unlike individual stars or clusters, these formations are not singular objects, but assemblies of matter spanning enormous distances, yet they are measurable and observable. Their discovery is the result of decades of redshift surveys, large-scale imaging projects, and increasingly sophisticated simulations. One of the most well-studied structures is the Sloan Great Wall. Discovered in 2003 using data from the Sloan Digital Sky Survey, it stretches approximately 1.4 billion light-years and contains thousands of galaxies organized into multiple superclusters. The wall is a network of dense clusters, filamentary extensions, and connecting galaxy groups, forming a massive contiguous structure. The Hercules Corona Borealis Great Wall was first identified in 2013 through gamma-ray burst mapping. This structure spans an estimated 10 billion light-years, making it the largest known structure in the observable universe. It is primarily traced through the positions of gamma-ray bursts, which serve as beacons for massive galaxies distributed along its filaments. It occupies roughly a quarter of the observable universe's diameter. The CFA2 Great Wall, one of the earliest discovered cosmic walls, extends approximately 500 million light-years and contains numerous clusters and superclusters. It was identified in 1989 through redshift surveys conducted at the Harvard-Smithsonian Center for Astrophysics. This wall revealed for the first time that galaxies could be arranged into sheet-like formations with significant voids separating them. The CFA2 Great Wall consists of multiple dense regions, each with thousands of galaxies, and its elongated structure shows how matter flows along filaments toward gravitational nodes, creating planar arrangements across vast distances. Filamentary superstructures include the Perseus-Pisces supercluster chain, a filamentary network stretching over 400 million light-years, connecting dozens of galaxy clusters. The Abell 426 cluster dominates its core. X-ray observations of the intercluster medium reveal vast reservoirs of hot gas, while gravitational studies suggest the presence of substantial dark matter, accounting for most of the filament's mass. The Laniakea supercluster spans approximately 520 million light-years and contains around 100,000 galaxies, including the Milky Way, bound by a shared gravitational basin. Its discovery in 2014 relied on mapping galaxy velocities rather than just their positions, revealing a coherent flow toward the Great Attractor, a dense gravitational node. Laniakea has an estimated mass of 10-17 solar masses. The Hercules supercluster contains over 200 clusters of galaxies across 330 million light-years. It lies approximately 500 million light-years from Earth and has strong filamentary connections to neighboring superclusters. Its member clusters display velocities of up to 1,500 kilometers per second. Observations in X-ray and radio wavelengths detect hot plasma flowing along filament. Some of the largest structures are identified not by visible galaxies, but through indirect traces, such as hydrogen gas and dark matter. The giant GRB wall, detected through gamma-ray bursts, and the Sloan Great Wall are traced using these methods. Radio and X-ray observations reveal filaments filled with hot gas, magnetic fields, and cosmic rays, all of which extend for hundreds of millions of light-years. These components contribute significantly to the total mass and gravitational pull of these formations. The mapping of these record-holding structures has been aided by increasingly sophisticated simulations. Projects like the Millennium Simulation and the illustrious TNG project replicate the evolution of the universe over 13.8 billion years, producing filamentary networks, walls, and clusters consistent with observations. These simulations predict that such enormous structures arise from tiny fluctuations in the primordial universe, amplified by gravity over billions of years. They also indicate that even larger structures may exist beyond the observable horizon, outside the range of light detection. Filaments and walls not only define spatial extent, but also influence galaxy evolution. Galaxies within dense walls often exhibit suppressed star formation, while those along filaments may continue active star formation due to inflows of gas. Galaxy mergers are frequent at the intersections of walls and filaments, fueling active galactic nuclei and producing massive elliptical galaxies. For example, in the Sloan Great Wall, clusters like Coma and Abell 1367 lie at dense intersections where gravitational interactions are intense, reshaping galaxy morphology over billions of years. Even within these enormous structures, hierarchies exist. Superclusters connect via filaments, walls connect superclusters, and all are embedded within the larger cosmic web. Observations of the Cosmic Flows Survey and the 2DF Galaxy Redshift Survey show that these structures are interconnected through gravity and cosmic flows, forming a continuous network across the observable universe. The discovery of these record-holding structures continues to expand astronomical observations. As surveys extend to greater distances, astronomers have identified new walls, filaments, and superclusters previously hidden by observational limits. The Vela supercluster, discovered at approximately 800 million light-years away, contains thousands of galaxies spread across a region more than 200 million light-years wide. Its discovery required careful mapping through regions obscured by the Milky Way's disk. Energy also plays a role on these scales. Collisions between clusters within walls and filaments generate shocks in the hot gas, heating it to tens of millions of degrees. Observations using the Chandra X-ray Observatory and the XMM Newton satellite reveal this energetic activity. Magnetic fields stretch across filaments, influencing cosmic rays and the movement of gas over millions of light-years. The Sloan Great Wall, Perseus-Pisces chain, and Hercules Corona Borealis Great Wall are among the largest structures observed, spanning billions of light-years and containing billions of galaxies. These formations exert gravitational influence over vast regions of space. The observable universe contains all known filaments, walls, superclusters, clusters, and galaxies within a measurable cosmic horizon. The observable universe. The observable universe represents the ultimate measurable scale in existence, encompassing every galaxy, cluster, filament, and wall that humanity has been able to detect. Stretching approximately 93 billion light-years in diameter, it contains an estimated 2 trillion galaxies, each with billions to hundreds of billions of stars. Unlike individual cosmic structures such as superclusters or the largest walls, the observable universe is not a single object, but the totality of all matter and energy that can be observed from Earth, bounded by the finite speed of light and the age of the universe. Its enormity is both awe-inspiring and essential for understanding the true scale of existence. The observable universe exists within the larger cosmos, but its boundaries are defined by the distance light has traveled since the Big Bang, approximately 13.8 billion years ago. Because space itself is expanding, galaxies currently hundreds of billions of light-years away can still be part of the observable universe due to the stretching of space. This expansion means that the light we see from the most distant galaxies began its journey over 13 billion years ago, allowing astronomers to peer into the universe's infancy. Instruments such as the Hubble Space Telescope, the James Webb Space Telescope, and large ground-based observatories have provided increasingly detailed images of these distant galaxies, revealing star formation, cluster assembly, and the earliest cosmic structures that evolved into today's cosmic web. Roughly 5% of the observable universe consists of ordinary baryonic matter, including stars, planets, gas, and dust. About 27% is dark matter, invisible yet detectable through gravitational effects such as lensing and galactic rotation curves. The remaining 68% is dark energy, the force driving the accelerated expansion of space. Dark matter and dark energy dominate the universe's mass-energy content and determine its structure, expansion rate, and evolution. Ordinary matter forms only a small fraction of the universe's total content. Galaxies within the observable universe are organized hierarchically. Stars form galaxies, galaxies form clusters, clusters assemble into superclusters, and superclusters are connected through the cosmic web's filaments and walls. Surveys such as the Sloan Digital Sky Survey and the 2DF Galaxy Redshift Survey have mapped millions of galaxies, revealing that the largest known structures, including the Sloan Great Wall, the Hercules Corona Borealis Great Wall, and the Perseus-Pisces supercluster, are all contained within this observable volume. Estimates suggest that a single cubic megaparsec of space can contain dozens to hundreds of galaxies, depending on its location within filaments, walls, or voids. Galaxy clusters, which can contain thousands of galaxies and trillions of solar masses, populate the observable universe in vast numbers. The Virgo cluster, located about 53 million light-years away, contains over 1,300 member galaxies and is part of the larger Laniakea supercluster. Similarly, the Coma cluster, situated roughly 321 million light-years from Earth, hosts over 1,000 galaxies and exhibits significant X-ray emission from hot intracluster gas. These clusters are gravitationally bound nodes within the cosmic web, and collectively they account for a substantial fraction of the universe's observable mass. The observable universe also reveals large-scale motion. Galaxies and clusters move relative to one another due to gravitational attraction and the expansion of space. The local group, including the Milky Way and Andromeda galaxies, moves at approximately 600 kilometers per second toward the Virgo cluster. Larger flows, such as the movement toward the Great Attractor within the Laniakea supercluster, involve hundreds of thousands of galaxies across hundreds of millions of light-years. Voids occupy the majority of the observable universe's volume. These underdense regions can span hundreds of millions of light-years and contain relatively few galaxies. The Botas void and the Eridanus supervoid are prime examples. Voids affect gravitational flows, galaxy evolution, and the distribution of dark matter within the universe. The age of the observable universe can be estimated from the cosmic microwave background, the afterglow of the Big Bang, which has traveled for 13.8 billion years to reach us. This radiation, detected by satellites such as COBE, WMAP, and Planck, reveals minute temperature fluctuations corresponding to regions of slightly higher or lower density. These fluctuations correspond to the initial density variations that led to the formation of large-scale structures. Stars radiate large amounts of energy, with the Milky Way containing an estimated 100–400 billion stars. Active galactic nuclei, powered by supermassive black holes such as the one in M87, with a mass of 6.5 billion solar masses, emit energy equivalent to trillions of suns over their lifetimes. Cosmic rays, magnetic fields, and diffuse X-ray and gamma-ray backgrounds contribute additional energy within the universe. These energetic phenomena are observable and measurable by astronomers. Dark energy causes the accelerated expansion of space, meaning regions of the universe currently visible will eventually recede beyond our observational horizon. Galaxies currently billions of light-years away may become inaccessible over time as space expands. The observable universe contains black holes of various masses, including stellar mass black holes up to tens of solar masses, and supermassive black holes reaching billions of solar masses. Neutron stars, magnetars, and other exotic objects populate galaxies, while massive galaxy mergers release gravitational waves detected by LIGO and Virgo. Clusters of galaxies contain hot gas exceeding tens of millions of degrees Kelvin, emitting X-rays across millions of light-years. These phenomena are observable and measurable across the universe. Estimates suggest that the observable universe contains between 1022 and 1024 stars. Combined with planets, interstellar gas, and dark matter, this contributes to the universe's total mass energy content. The universe exhibits a hierarchical structure from individual particles to galaxy clusters, spanning approximately 27 orders of magnitude in scale. Finally, the observable universe represents the ultimate context for all previously discussed structures. It contains the cosmic web, filaments, walls, superclusters, clusters, galaxies, stars, planets, and exotic objects within a single measurable volume. Observations of this universe provide the largest dataset humanity can access, and understanding its structure and contents allows scientists to quantify the limits of measurable largeness. While the universe beyond this observable horizon may extend infinitely, the observable universe itself remains the largest fully charted structure in existence, encompassing all known matter, energy, and cosmic history.